I'm a bit obsessive about my work and often dream about aspects of my job. One day I had a wonderful dream. My slumber was interrupted by a presenter on the radio telling me about the new lighting of the Sistine Chapel. The man in my dream said something like this.
50 hidden arrays of light-emitting diodes, LEDs, which not only save power but have been fine-tuned to illuminate the pigments used by Michelangelo evenly and harmoniously. The restoration carried out 20 years ago can only now be seen in its full glory with the new lighting.
However, this was no dream. It was reality. The Sistine Chapel has been relit, and the change of lighting is seen as significant enough to merit a segment on BBC Radio 4's flagship morning news programme. This is a truly strange world. Lighting design, as opposed to lighting technology, is making the mainstream news. What is beginning to catch people's attention is that lighting can alter our perceptions of well-known artworks, and that light has the power to reveal hitherto unseen aspects of the world around us. Whilst this is not a surprise to those with experience of light in the heritage environments, it's normally something that we have a hard job explaining to other people, even museum professionals. The relighting of the Sistine Chapel could be about to change all of that. It could reveal the hidden world of conservation lighting to an audience of millions. There's a dichotomy at the heart of heritage lighting, and in particular museum lighting and gallery lighting. That dichotomy represents the conflict between the needs to preserve the exhibits on display and for the audience to actually see those exhibits to their best abilities. We need to remember that vision is our principal sensory experience of artworks in museums and gallery settings. There's very little that we can touch in a museum. It is frowned upon. So vision is very important, but vision is very restricted in museum and gallery settings. In architectural lighting, such as here the Grand Mosque in Abu Dhabi, light can be the hero. It is the intangible medium that makes physical space visible. We relish the light, the reflections, the sparkle within environments like this. We don't often have these options in museum lighting. In architectural lighting, we are usually tasked with delivering a minimum quantity of light for a given task. In museum and gallery lighting, we are usually working with maximum illumination limits. This is because in the museum, light is both a hero and a villain. Light can be the hero that allows us to see the detail and the beauty of the exhibits, but exhibition lighting also has an unintended consequence. Light-induced damage to artefacts is irreversible. Damage can include fading of pigments and physical degradation of materials. We need lighting that maintains good conservation standards. But what is conservation lighting? Conservation lighting is truly a compromise between visibility and preservation, that dichotomy at the heart of the museum. Different materials have different sensitivities to light energy. Length of exposure can also be limited. CIE in 2004 gathered together the best practice from around the world in terms of conservation lighting and recommended 3 bands of object sensitivity: low responsivity, maximum illumination of 200 lux, medium responsivity, 50 lux, high responsivity, 50 lux with reduced display time, to reduce the total quantity of light that may damage the exhibit. These are very low levels of light compared to what we're used to in normal architectural environments. But interestingly, not everyone has the same standards. Although there are now international standards as proposed by the CIE, individual institutions still maintain their own standards. They have different standards for different materials, and they don't always agree with everyone else's standards. So the Victoria and Albert Museum in London, their specifications for light-stable materials, for light-durable materials, and for light-sensitive materials do not necessarily agree with the CIE recommendations. These standards were created before the CIE 2004 recommendations. However, they're still in use by the V&A today, even for brand new build museums. Conservation lighting is what we expect in museums, and particularly with very sensitive exhibits. But should we really expect conservation lighting to give us this kind of environment? Is this what we really need? This example here is also conservation lighting. Every single exhibit in this image is actually illuminated to 50 lux. This is not fantastically clever photography. This is actually a real representation of what it actually feels like to walk into this space. Conservation lighting can be done in a way that does not need to feel dark and gloomy. There's a lot more to lighting in museums and galleries that we can explore in great detail. There's a lot of detail that we tend to skip over when we actually walk around the museums and examine the lighting. Lighting to reveal and conceal is a fantastic opportunity that we have as designers. Excellent exhibition lighting will often look effortless, with exhibits perfectly illuminated in comfortable and relaxing surroundings. But getting exhibition lighting right is not always easy. These images from Iona Museum in Scotland, with lighting by Kevin Shaw Lighting Design, give us the impression of what we expect of quality lighting in museums. If we visit lots of good museums, we see lots of good lighting. We expect that this is easy, but that's not always the case. Lighting angles can make a dramatic difference to the interpretation of an object, such as these early Christian carved stones. Grazing light can reveal shallow carvings and textures that can be difficult to see in any other circumstance. The importance of getting the lighting angles correct should not be underestimated. As a test, I relit these objects with direct front illumination, and as you can see, the whole exhibit, the intention of these objects actually being on display, the carving within the stone, completely disappears in some cases. Even the material seems completely different. The stone at the bottom left becomes very shiny and glossy, with the mica embedded in its surface. The large stone behind becomes an exhibit of stains, probably from lichen, because this stone used to be outdoors. But essentially the carving has gone. The lighting angle is critical to reveal the actual exhibit. This is something that I explored further in Maze How Neolithic Chambered Cairn in Orkney World Heritage Site in the UK. The Neolithic tomb was actually broken into by Viking invaders much later. And those invaders, like all invaders, scratched graffiti on the walls. Exploring the use of different angles of light to actually reveal or conceal and see how critical the angle was very revealing. Small changes in lighting angles from this image, which was purely front lit, to 45-degree angle, to a 30-degree angle, through to a 15-degree angle. We go from very shallow inscriptions that are barely visible through to being completely revealed to again being concealed when the angle gets too shallow, where the texture of the stone and the rock that these inscriptions are carved into becomes more dominant through the depth of the shadow. In the tomb itself, small parties are taken in by a guide. The guide uses handheld torch to reveal the carvings and inscriptions one at a time as part of the verbal interpretation of the site. This is one of the most famous carvings, often called a dragon or a lion, no one's really sure. Again, it was carved by Viking invaders who broke into the tomb. This carving is small and can really barely be seen within the tomb. It's only when the torch is switched on at just the right angle it jumps out. With a change of lighting angle, a story that could be about Viking runes can become a story about the geology of the stone used to build the tomb itself. All of these stories are possible just by changing the light. This is part of light as an interpreter. The opportunities that we have as designers and practitioners with light, to use light to tell a story, to reveal more than the object itself can possess. Just as with full-size architecture, small models, such as this display from the Architecture Gallery at the V&A Museum in London, they can be interpreted in a way as if they were real pieces of architecture. This scale model is not large, but the illumination of it was deliberately created to be architectural in look and feel, as if it was a real building. Fibre optics take the place of in-ground uplights. This model of the Alhambra Pavilion was therefore rendered as if it was a real piece of architecture, full scale. Difficult objects such as these cinema projectors and movie cameras displayed in the Royal Museum of Scotland are actually, although they're completely black almost all over, they're still 50 lux objects. They're very sensitive to light. So the maximum illumination they could receive was only 50 lux. And when everything is black, that means almost nothing comes back. As part of the interpretation of these objects, and to actually enhance the display, dramatic uplighting was deliberately used to add another dimension to the objects, a direct reference to newsreel movies from the 1940s and 1950s. In Hindu temples, the god Shiva is often represented as a dancing statue, a figure in full flowing movement. Where they're normally seen within the temple environment, the lighting is dim, coming from oil lamps. This flickering, guttering flame makes the shadows of the figure dance on the walls behind. This movement, this bringing alive of the statue, of the solid, of the static, is an incredibly important part of the original setting of this statue. Within the museum setting in St Mungo's Museum of Religious Life in Glasgow, it was very important for us as the designers to actually represent this statue the way it should be experienced. Static exhibition lighting was not going to be good enough. The oil lamps are practicals. They're not actually illuminating anything at all. But above and in front of the statue, there are two slots. Within these slots are custom-built light fittings with motors and twin lamps. And these twin lamps shine through textured glass which slowly revolves in front of the lights. The flickering light that this produces reproduces the effect of the dancing shadows on the wall behind. It's a simple device, but incredibly important to restore some of the interpretation to the object that's lost as soon as it's removed to the museum setting. There's something very fundamental about light and the way we actually respond to light. Phototropism is quite often a curse within low light environments. Phototropism is a tendency for the eye to be drawn to the brightest area in our field of view. This is a very natural thing. People like shiny things. Light fittings, luminaires, lights produce shiny stuff. It should be great, but it's not. Research published in April this year attributed the human attraction to shiny and glossy materials to an innate need for water. Whether that's the case or not, it actually causes a problem sometimes. Good use of highlighting as a subtle aid to wayfinding can really enhance the atmosphere of museums and gallery spaces. But shiny is not always good. Where the exhibits themselves are highly polished, reflective or glossy, the use of lighting has to be very carefully controlled. Stand in one place in this room in the Louvre and the painting is perfectly evenly illuminated. It is well lit, but move in closer to look at the detail and the title below and suddenly large parts of the image are concealed by glare. The veiling reflections in the oil painting and in this display case mounted in front of a window both go to conceal the objects that we are actually there to look at. In this example in the Orkney Museum, a carved stone is in the display case in front of a large window. The photograph mounted next to it is actually of the same object, lit with good low-angle lighting to reveal the carving. Ironically, neither the photograph nor the object itself are actually visible because of the veiling reflections. Layers and layers of lighting horror can be created by reflection and poor lighting. In this display case from the Museum of Scotland in Edinburgh, and this is a brand new installation, we have cased-up fluorescence, the brightest thing in our field of view when we look into this case. All we can really see is the diffusing glare of the fluorescence. Beyond that, we see specular reflections shining off the front surface of the glass from track spotlights mounted behind us. We also have a large reflection from a daylit walkway at high level above, where two adult figures and one child stand looking over the balcony. All of these reflections are much brighter than the exhibits that we're actually trying to see, and therefore these reflections are helping to conceal what it is that the museum is all about. Part of the problem is the light levels that we're dealing with. Where we have low light levels, reflections can become much more of a problem. But how do we go about quantifying light for conservation? If 50 lux is so critical, how do we qualify that? Well, this is the norm world over. Illuminance meters to measure the visible light incident on the surface. But do these meters, no matter how good the quality or how expensive they might be, do they really directly measure what we need to know? They are not a direct measurement of light energy. They're something subtly different. Matching the spectral response of the CIE photopic observer is the gold standard for illuminance meters. This is what very high quality meters attempt to replicate, the spectral response of the human visual system to visible light. But how good are these meters at actually achieving this? Well, high quality meters match this curve very well. But in these tests by ProLight technology, looking at high quality and lower quality illuminance meters, you can see that there are subtle drifts where the curves do not quite follow the ideal. The CIE photopic observer is very precise, but these meters drift enough to be of concern. Even very, very good illuminance meters cannot precisely match the V lambda curve. It's difficult to see from this chart exactly what the errors might mean, but where errors are actually extrapolated and put into spectral mismatch, as we have here, something dramatic comes out. Within the centre, the peak of vision, the match is almost exact. There is nothing to worry about. But the further we drift from the centre, from the peak of V lambda, the more the errors are introduced. These errors can be underreported or overreported. At the low end, around 460 nanometers, these two illuminance meters are underreporting by 25 and 30%. At the other end of the spectrum, 660 nanometers, one illuminance meter underreported by 40%, the other one overreported the level of illumination by 75%. These are important because 460 nanometers is pretty much the peak of a blue LED. There is also a significant peak for cool white phosphors in this part of the spectrum. If our illuminance meters are underreporting by 25 to 30% the quantity of light at this peak, how can we have any confidence that we're getting a real quantity of light measured? Illuminance is not enough as a measurement. And indeed, museums do not rely solely on illuminance. Ultraviolet light is incredibly damaging to most objects, and ultraviolet is excluded as much as possible. But measurements of illuminance and ultraviolet are not really good enough indicators of potential damage to objects. Individual materials have different sensitivities to light, but damage increases as wavelength decreases, with ultraviolet being the most damaging part of the light spectrum. Moving on from illuminance, there's something else that can actually be measured. It's the relative damage, the potential for damage compared to other light sources. In this study from the National Gallery in London, they took the filtered daylight that was inside one of their principal galleries and used that as their standard high quality illumination. They measured the colour temperature, the colour rendering index, and the relative exposure. As we can see towards the bottom of this chart, there are two LED fittings, both of which managed to score some 40% less damaging than the reference light source. There is something different happening here. There's something that is possible with LEDs, with good quality LEDs, that was much harder to achieve in the past. Perhaps we can actually start to think about illuminance in museums in a different way. We can think about the potential for damage rather than just straight illuminance levels. To actually look at the spectral power distribution of a series of light sources that are common in museums, we have MR16 low voltage tungsten halogen. We have 14 watt LED produced by ERCO. We have a Staccato LED Artist series. We look at the spectral output of these sources and we see how little they represent the CIE standard observer for photopic vision. And yet, what we're measuring these sources with is a meter that is trying to replicate the CIE standard observer. But as you can see, in all cases, the peaks of these light sources are actually outside the peak of the illuminance meter. It cannot represent the truth of what's actually there. Accurate quantification of light in the museum needs to use actual spectral measurements instead of the measurements that we get from illuminance meters. When it comes to colour rendering in museums and galleries, the received wisdom is that the highest colour rendering light sources are the best option for lighting museum exhibits. This is how I learned my trade. High numbers are better. But the advent of LEDs has brought people to question the quality of these metrics, colour rendering index in particular. Something else is happening in museums. If you actually take a chart and look at what recent builds are actually using in terms of light, there's something strange happening. For a start, in all these museums, the variation in colour temperature is quite significant. There is no standard colour temperature for these leading museums. Colour rendering index is largely very high, 90 or above. But there's one significant standout figure here. The National Galleries in London spent a long time testing lots and lots of different options for LEDs. In the end, they took the decision based on the visual quality. They chose the luminaires and the light sources that produced the best visible effect for their exhibits. As it turned out, the colour temperature was 3200. The colour rendering index was 85, significantly lower than any of these other museums. Is there something about the colour rendering index that means it's not really a good enough predictor of colour quality, particularly when it comes to museum environments? Another thing to take into account is all of these, apart from the very last one, the Osram installation at the Sistine Chapel, just recently unveiled, use white LED sources. But the Osram solution uses a custom blend of red, green, blue and warm white LED. The target colour temperature is possibly around 3250 Kelvin, although I can't be sure. The colour rendering index, I don't know. But what's colour rendering index all about? Why is it possibly not working for us after all these years? The original colour rendering index was based around 8 colour samples, 8 pastel shades. The standard is 50 years old and compares samples to a reference light source, tungsten normally. With the advent of LEDs, this average was no longer good enough, that reds, in particular saturated reds, could be rendered very differently by LEDs, but the colour rendering index did not seem to take this into account. So R9 adds a separate saturated red. Other samples have been added as well, as more saturated versions up to 14, to give an extended colour rendering index in an attempt to create something that produces something more representative of what we actually see. Other possible solutions for measuring colour rendering are the colour quality scale and the gamma area index. But in all these cases, we are still measuring against a standard, a reference source, which is actually no longer the light source of choice in museums. We could take 3 different sources, say red, green and blue LEDs. We can mix these in different quantities to produce any colour within the gamut triangle. In theory, we can mix these red, green and blue LEDs to match a 3000 Kelvin blackbody radiator. We can hit the curve exactly. But what happens if we actually do that? Well, here's an RGB luminaire, the spectral response when set to try and match 3200 Kelvin. We managed to do it very closely indeed. But look at the colour rendering index, 26. It's nowhere near 90, it's nowhere near 80. It's pathetic. But the colour appears to be 3200. The gaps in the spectrum here are traditionally seen as a problem. That's why the colour rendering is so low. But could it be that these gaps present opportunities to reduce damage where we don't need to actually produce light energy? The 16th century frescoes painted by Michelangelo in the Sistine Chapel are very colourful after their restoration. The 50 new LED luminaires, instead of using phosphor white, they use red, green, blue and warm white LEDs. They're individually tuned to suit the pigment of the frescoes. This custom RGBW mix is likely to have a relatively poor colour rendering index. But the researchers instead created their own Sistine Chapel Colour Fidelity Index, which is based not on the sample chips used for colour rendering index or colour quality scale, but on the colours that are actually used in the fresco itself. And based on that, they selected the correct lighting. We're entering an interesting age in terms of heritage lighting. New things are possible with LEDs. We might question the quality of our metrics, but other things are amazing possibilities. Virtual restoration is one. A project that I'm currently working on for Historic Scotland is based in the ruins of Elgin Cathedral in the north of Scotland, a 13th century Gothic cathedral. Tombs of former bishops adorn the perimeter walls. The bishops' tombs are adorned by carved stone effigies. One of these effigies of an unknown bishop forms the centrepiece of a new exhibition. The project I'm involved in currently is to virtually restore the colour to the object. This project began in 2010 when actually exploring the conservation collection for another project. Looking at the carved stone effigy, there's an incredible amount of detail in the carving. But what is not seen by most observers is that there's actually fragments of colour there's fragments of paint left on the object. They're faded, they've been painted over, they've been scratched off and worn away from years of neglect and erosion. But conservators and curators have actually recreated the original colours as a colour sample here, ranging from vibrant crimsons through to greys, pale blues and golds. Traditionally, as a lighting designer, my tools of the trade would normally be high quality luminaires such as these to illuminate an object such as this. But in this case, that was not enough. These luminaires cannot restore the colour that is not there. But a digital projector with long-life LED and laser-based light sources could provide unique opportunities not normally available to a lighting designer. And indeed, that is what we're doing in this project. The projector allows you to do things that you could only dream of as a lighting designer, to accurately slice out sections of the object. We can isolate the illumination of individual fragments to tell the story and narrate the object. Working with computers and actually drawing virtually live on top of the object gives us the opportunity to do amazing things and return the colour to the object. This is not just something that I'm working on alone. I recently discovered that actually a very famous artist suffered a similar problem with fading pigment. In 1963, 5 paintings by Mark Rothko were installed in a very bright, sunny room at Harvard University. It was not long before the paintings were very sun damaged, beyond any kind of repair. In January this year, they were restored using digital projectors to restore the faded colours to the painting. Along with white illumination, subtle additions of colour are created by the digital projectors to put back some sense of what should have been there in the first place, the colour that's been lost through time. At Elgin Cathedral, whilst the traditional white light illumination of the object may look something like this, the digital projection allows other magic to appear. A virtual spotlight can be moved across the projector to pick out different parts of the object to tell the story. The light can change. Text can be projected directly on parts of the object to identify things and bring the story closer to the audience. A sequence can be enacted to create a story that gradually restores the colour of the original vibrancy of the fabrics and materials to the object. This is how this object was intended to be seen, with this level of vibrancy and saturation of colour. Over time we have lost that. We see this as just a pure stone object. Digital projection can allow us to restore this virtually. With digital projectors, it is possible to tune the light source to suit the pigments being illuminated. We can therefore adjust the illumination to maximise reflectance and minimise absorption, thereby reducing potential damage. Is this the future for lighting design in museums, galleries and heritage environments? It can't be everything, but it does allow us to do things that we never dreamt of in the past.